here I'll be talking about a method for collecting event-based data sets for pose estimation. So arguably one of the reasons artificial neural networks have been so successful is that they've had access to a lot of very good data sources and a lot of data. For example, ImageNet, where we have a collection of 1 million+ images for classification. The Pascal VOC dataset for segmentation, but there's relatively fewer datasets, key datasets for spiking. There are some. We have the IBM gesture dataset, and there's also a spiking neuromorphic version of the NNEST dataset. But there's a lack of infrastructure for collecting large event-based datasets. We can collect a lot of data, but the actual automated labeling procedure makes it difficult to collect large data. So what we're trying to do is develop a human helper for handling, manipulating tools and passing them to a human subject. We're doing this with the team in KTH. So we have our setup is a set of 8 Vicon cameras. Vicon is 3D tracking. A set of two DVS cameras. For anyone who doesn't know, DVS cameras, event-based vision. They pass only pixels that change in brightness intensity, very power efficient. So the idea is that we project the meshes, the STL meshes of our props into Vicon 3D tracking space based on known marker locations from the STL file and from the Vicon tracker. And from there, we then project onto the DVS camera planes, again, based on known camera position and orientation of the DVS cameras. So one of the problems we've had with using DVS cameras together with the Vicon, how the Vicon 3D tracking system works, it shines an infrared strobe light onto reflective markers, and then it reads the reflection back and triangulates the position. But the infrared strobe from the Vicon system is picked up by the DVS cameras. It causes a saturated frame, so no data, nothing is visible from the DVS cameras when the Vicon is active. So the solution was to switch off the strobe, and we custom 3D printed our own props with hollow insides and very low power infrared tracking LEDs with power sources. These low power infrared lights can easily be filtered by adding infrared filters to the DVS cameras. These props are available online on the link there. So, as I said, we also need to know the position and orientation of the DVS cameras in order to project onto them. So what we need to do is, using a flashing marker, we record on the Vicon system, tracking system, and the DVS cameras at a number of locations. We use the flashing on the Vicon active one so that both the DVS cameras can pick up the flashing and the Vicon system can pick up the location of the markers. And using these points through optimization, we can compute the best rotation and translation from 3D Vicon space into 3D camera-centric space, and then project onto the DVS camera plane using a standard pinhole model. Okay, so here's an example recording. Here's some very spooky flying event props. It's 2 cameras. We can have multiple props in view, and we're able to generate segmentation masks and of the events and RGB frames. And we're also able to have translation and rotation labels of the props. Sometimes the Vicon system fails to pick up each prop. So missing data is recovered by extrapolating the poses based on prior known data. So in the video, we can see the red, you might just be able to see on this camera, apologies if not, green events are those that are outside of prop label masks, whereas red events are on prop label masks. And we also have the same for the RGB frame here. Okay, so we've collected a sample data set online. So we have 9 separate 30-second recordings of suspended moving props. We have a screwdriver, a hammer, and a spanner. They're all stored on HDF5 format on the link given. And the processing code is available online at GitHub. So each recording is a HDF file directory. And within each directory, there's frame.h5, which contains the RGB frame data, as well as the segmentation mask for it. We also have an event HDF5 file containing all of the events labeled to what prop they belong to or background. And we also have another HDF5 file for pose. That's camera-centric rotation and camera-centric translation, as well as global rotation and translation. Okay, so an example of what we can do with this data. So this is object detection. And what we've done here is we have bin our events into 21 millisecond frames. We have data augmentation to expand the data set slightly. We train a VGG-like model as an ANN using transfer learning, and we then convert this trained in ANN into an SNN using few spike conversion method. That's a spike timing conversion method that's developed by Stockel and Mass. So, and we get the confusion matrices also. So on the bottom left, that's the, we get 89% accuracy overall on this particular model. So the bottom left is it's multi-label classification, and this is per prop confusion matrices. And on the right, we have the confusion matrices for each prop, and also with or without each other prop. So on the y-axis, we have the target label, whether the prop is there or not. And on the x-axis, we have whether the model predicts that it's there or not. So we see, I'll just move this out of the way. So we see if a prop is present, but no other prop is present, the model performs nearly perfectly, 49% for hammer, and for screwdriver, that's 50 and 48%. However, certain cases, such as when a prop self-occludes each other, when a prop is rotated at a funny angle, the hammer can look like for instance, a screwdriver. And also when the prop stops moving, no events are generated, so it's unable to disambiguate. In particular, the spanner, when the spanner is not present, but both other props are present, the model often predicts that a spanner is also present because presumably it looks like a spanner, the other two props. Okay, I made this out of the way. So some issues to work through. Again, no events when the props stand still. Also, it's difficult to disambiguate props at certain angles. For instance, if a hammer is rotated sideways, it can look like a spanner. So other problems are occlusion, noise, and the presence of other objects, such as a human walking past the field of view. So to deal with these problems, we're going to be looking into integrating detection and pose information over time using the temporal aspect of the data. And we're also going to be working on estimating prop translation and rotation, as in addition to whether the prop actually exists or not based on the data. And we'll also be working on expanding the sample data set. So, thank you very much.